some kind of power failures in my area. Therefore, I couldn't have this lecture hour. So sorry for the inconvenience. Okay, we can continue from this topic, right? Before that, we have discussed about the basics, very basic things in multimedia, then different types of multimedia, then images, different types of images, then typography, right? From this week, this session, we are going to discuss about video compression, right? Then simply we can say video is a collection of images, right? Frame, we can say frame is an image, right? We can change images with the respect to the type. Then we can see some moving objects in our video, right? This is the dynamic one. And we can say simply video is a collection of continuous images, right? Then why we need compression, video compression? What is the purpose of this topic actually? Why this is very important in the dealing with multimedia? In very first lecture, I mentioned you uh, uh, in multimedia, we have to transfer or save your project or data inside the local file storage, or you have to transfer one place to another place through a network, right? Then these video files could be have a large, huge capacity, right? In nowadays, we have a good quality of videos in or films in internet. When we download a video or a movie, let's say 1 hour and 30 minutes video, it's would be around 1.5 GB, right? It is after compression actually, right? Okay, let's try to calculate this one. Right. Let's assume you have a movie video without compression, right? It has this frame size, 720 into 480 pixel. This is 480p quality video, right? This is 480p quality video, right? The frame size is 720 pixel with 480 pixel height. Then 30 frames per second. 30 frames per second. What is this one means? 30 frames per second. It means when you play this video, or when you display this video through a video player, it will show 30 frames at a second. Within a second, it will change 30 frames, right? Then total duration of the video is 90 minutes. Then this is full color. Full color means it has 3 channels: red channel, green channel, and blue channel, right? Then let's try to calculate the capacity or the file size of this video file. Let's calculate, try to calculate the total number of pixels in a single frame. 720 into 480. It gives total number of pixels in a single frame. Then it has 3 frames, right? Because it is full color, it means it has three different channels. Then we have 3 different 720 into 480 frames for a single image, single frame, right? For a single display or single, we can say a single instant, we have 3 times this amount of pixels, right? Then let's try to calculate how many pixels are used in a second. Let's say 30 frames per second. It means for a single second, it shows 30 frames. Then we have to multiply this one by 30. Then this one gives the number of pixels that are used for this video for a second, right? Then this video has 90 minutes. This is for second. Then when we multiply this one by 60, this one will give a number of frames for minutes, right? Then when we multiply this one by 90, this one will give the total number of pixels that are used for this 90 minutes duration, right? Right? Clear? Let's try to multiply this one. 720 into 480 into 3 into 30 into 60 into 90. Okay, it gives this amount. This is in bytes, right? This is in bytes. Then when we divide this one by we divide this one by 1,000. This one will give in kilobytes. When we divide this one by 1024, this is in megabytes, right? Further, we divide this one from 1024. This one will give the amount in GB, right? It gives 160, around 160 GB, right? This is the capacity or the file size for this video, for this movie. Let's assume this amount of video you are going to download. You have to wait more than 1 month, because most of you have maximum 100 GB data package. In most cases, right? Then you have to wait for a movie for 2 months, right? We can download 100 GB in this month, and another 60 GB we have to wait until next month, right? Then this is the how important video compression is, how important in multimedia systems, right? Then you can see what is the importance of this topic, right? We have to compress video without downloading or transfer one place to another place, or store somewhere in local file directory, right? Then we can move to the next one. Yeah, video compression. Video is I told you earlier, video is a sequence of images, right? Then in video compression, we can identify some similar frames in video, right? I will show you an example. Let's take this one. Okay, this is a video downloaded from internet. All right, so I'll post here. I'll post here and see. Let's assume this is a one frame, and this is another frame very close to each other, right? This is the let's say this is the 100th frame, and this is the 99 frame. You can see there are some similarities. See this sky among these two frames. See this sky. Most pixels are very similar. Water also, and some mountain ranges, mountain sites, all are very similar, right? In video compression, we are identify those types of similarities among these video frames. Then we are removing these pixels actually, right? We have a good quality video. Then we can identify using some kind of algorithms. Using these algorithms, we can find out the similar pixels, something like this, right? We can identify similar pixels. See these images, sky, area, both frames have similar, very similar content, right? Very similar pixel colors, pixel values actually, right? Water area also, and the mountain area, we can identify very similar areas, very similar pixel values. Then we can identify those uh, similarities, similar pixels using some algorithms, and we are going to reduce, or we are going to remove those types of similarities, similar pixels. Then we can reduce the file size without huge effect to the quality of the video, right? We have to keep in mind, we have to manage the video quality as well as the video file size, right? We can't reduce video size without considering the quality. We have to maintain the good quality of the video as well as we have to reduce the file size as well, right? Then there are two coding methods we have. First one is intra-frame coding and second one is inter-frame coding, right? Intra-frame coding and inter-frame coding, right? Intra-frame coding is removing spatial redundancy. What it means? See this image. This image also have similar areas. See this uh, sky area. It is almost similar. The pixel values are almost similar. Then when we identify the similar pixels, a specific frame itself, we can say it is an intra-frame coding, right? Only take a single frame and identify similar pixels itself in the single frame. We call it as intra-frame coding. Inter-frame coding means we are taking more than one frame and taking one as a reference and another one as a target frame, then comparing with the target frame and this reference frame, then identify the similar pixels and remove redundancies. We called it as interframe coding. Interframe coding. Intraframe coding means only consider single frame and identify similar pixels and removing redundancy. We call it as intraframe. Interframe means considering more than one frames at a time and taking one or two as a reference and single one as the target one, and comparing with the reference one, we can identify the similar pixels, right? Similar pixels and removing redundancy. We called it as interframe coding, right? Right. This slide is all very familiar for all of you. I'll show you this one in last week session as well, right? This is some commonly used codecs. You know what is the importance of codecs, right? In MPEG-4, it use H.263 or H.264 codec, right? And it has DivX or DivX Pro codec, codec, and other important codecs, right? We are going to have some exercises with FFmpeg codec as well. Therefore, that is the reason why I have bold it one. Right, this is very important for us. We are going to have some practical sessions as well using this codec. Right. Then let's see MPEG video compression. Right. MPEG video is video standards is established in 1988. Right. It is uh, standardized international it is what we called accepted by the ISO and IEC, and this is the official name. This is just only for your knowledge, right? It's not very important for this topic, right? This is just only for your knowledge. Then I mentioned earlier, we have 5 types of MPEG formats, MPEG standards, right? In MPEG 1, it is MPEG 1 standard is used for medias to store in local file system, right? MPEG 1 standard is used to store audio, video, and pictures in any kind of storage devices, right? MPEG 2 standard is used in televisions, right? Televisions and DVD, digital versatile discs. In MPEG 4 is a very widely used MPEG standard. It is widely used in different types of multimedia applications, right? Almost all multimedia applications used MPEG 4 video standard, right? Then MPEG 7 standard is used in some kind of search operations, right? Then let's say you are going to search something in a video. This video should be in MPEG 7 standard, right? Then MPEG 21 is offers with metadata information. Metadata information means we can't see metadata information in a video, right? But you heard this one. Let's say when we taking a photo, this photo contains the information about the device and the location, time, flight, information. We can't see actually, but the devices can read those things, right? Let's say someone taking unwanted pictures, let's say some place and publish them on social media. Then the related authorities can identify the metadata or extract metadata from these images and identify what is the person, who is the person that took those photos, right? These are the metadata. Metadata contains the IMEI number of the camera or the device, the location and time. Like those things will be included in metadata. In MPEG 21 standard, it offers metadata information for audio and video files, right? Those are the different types of MPEG standards. In this lecture, we are going to consider MPEG 1 standard video compression, right? This MPEG 1 video standard is used in video CD, VCD, and MP3 and MP2, right? Okay. When we consider or when we discuss about video compression, it is doing in this. We have to consider these 5 parts. In first part, we have to combine video stream and audio stream. Initially, it is in separate streams, right? We have to combine those video stream and audio stream. It could be a single data stream or multiple data stream. Then we can compress the video and then compress the audio. Then requirement verification. It means we are giving the requirements for a for this video to play somewhere else. Then finally, it will create a technical report on the software implementation of part 1 to 3, right? These are the very important parts when we are compressing MPEG-1 standards video, right? First, combining video and audio, then compressing video, then compressing audio, then fulfill the requirements and verifications. After that, creating a technical report, right? I will show you an example using Premiere Pro. Right, I will import or drag and drop a video from my local file system. Here you can see when I move this video among these video streams, you can see I can't move this audio and video separately. See, initially all these video layers and audio layers are combined each other. I can't move them, right? If I unlink those video stream and audio stream, then I can move those video stream and audio stream separately, right? I independently I can move those things, right? In video compression, if this video and audio is in separate streams, something like this, first of all, we have to link those things, right? We have to link those things. That is why here we can see, we can say as the first part, we have to combine video and audio inputs into a single data stream. Then we can video compression, we can work with video compression, then audio compression and requirement verification. Finally, technical creating a technical report, right? These are the very important parts of MPEG-1 compression. Right, in MPEG-1 video compression, first of all, we have to consider, we have to take group of pictures among the video. Let's say this is the video, this is the video. Then we have to find out some group of pictures. Actually, this picture means group of frames, right? Out of this group of frames, we can consider a single frame. Here we call it as picture, right? First, we have a video sequence or a sequence of pictures. Then out of this sequence of pictures, we can uh, get some kind of group of pictures. Out of this group of pictures, we can take a single frame. We call it as pictures. Then we can get a slice from this picture. We can get a slice. In this slice, we can consider macro block, right? This macro block contains a block, 4 blocks actually. Macro blocks contains block. One block contains 8 by 8 pixels. In totally 64-bit pixels, right? Uh, in a block, inside a block, it is 8 by 8 pixel. It means 64 pixels. In a macro block, we have 64, 64, 64, 64. Totally 120, 256. 256 pixels, right? Initially, we have a sequence of video or a sequence of images or sequence of frames. Then out of these frames, we can get a group of pictures. Then we can consider a picture. From a picture, we can consider a slice. This slice contains these types of macro blocks. This macro blocks contains blocks, 4 blocks. Single macro blocks contain 4 blocks. A block contains 8 by 8 pixels. Actually, here we are going to divide our frames into different frames for comparison, right? For the comparison, we are not going to take 1 pixel and 1 pixel comparison. We are considering a block, right? Actually, this is the smallest unit we are going to compare with other places or other frames, right? We have a group of pictures. Out of group of pictures, we can take a single picture. Then slice has some amount of macro blocks. Macro blocks have four uh, 4 blocks. Blocks contain 64 pixels, right? This is this smallest unit we are considering when comparison among single frame or a multiple frames, right? Then this is the another overview of the same thing, right? We have a video layer or video sequence. We can get a group of pictures. Out of group of pictures, we can get a single picture. We call it as picture. Then this picture we can get a slice. Slice contains more than one macro blocks. One macro block contain a block. Block is a 8 by 8 pixels. Totally 64 pixels. Right. Then video compression. I told you earlier, when we compare the similar pixels, we can consider only one frame or more than one frame, right? One frame or more than one frame, interframe or intra-frame coding, right? We can consider 3 types of group of pictures. First one is I frame, second one is P frame, and third one is B frame. I frame means uh, we are not going to consider another reference frame. We are only taking only one frame and identify similar pixels. It is mean by I frame. P frame means we are going to consider previous frame as the reference, right? In this picture shows this is the green one is the target frame. Previous one, this ash color one is the reference frame, right? We are comparing P frame, this frame and the previous frame to identify similar pixels. These frames we call P frames. Then B frames means we are considering previous frame and the next frame to identify the similar pixels. We call it as B frame, right? I frame, we are finding the similar pixels itself inside this single frame. Then P frame means we are considering we are getting a reference frame as the previous frame, then identify similar pixels among this previous frame and the target frame. In B frame, we are considering previous frame and the next frame and identify similar pixels. Then can someone tell me which frame will be uh, getting more compression? Which frame? I frame or P frame or B frame? Which one will give more compression, more similar pixels. First one or the second one or the third one? Which frame gives more similar pixels? You can put your answers in the chat. What frame gives more similar pixels?
B frames.
Yeah, B frame, exactly. We are considering two reference frames, right? It gives more similar pixels, not first one, right? B frame. B frame is the best one for video compression, right? Then let's take one by one and see. In iframe, I mentioned you earlier, we are going to consider macro blocks in same frame. We are only just considering the target frame and identify the similar macro blocks or similar pixels in the target frame itself, right? We can say it is a spatial redundancy. So we are using intra-frame coding when we consider the iframes, right? In p frames, it will consider the previous frame as the reference and consider or find out the similar macro blocks. But in this case, the very first frame is again a iframe because we don't have any kind of previous frame here to get the reference frame for the first one. Therefore, this one definitely an iframe. Then after that, this one could be P frame or B frame, right? We have previous one and the next one. Therefore, this frames could be P frame or the B frames. But very first frame should be a I frame because we don't have anything to get the reference for this frame, right? And the B frame, this is the best one for video compression or identify the similar blocks, macro blocks, right? B frame considering two reference frame, previous one and the next one, and compress or identify the similar blocks in the middle one. Okay, these are the very important steps in MPEG compression, right? First, reduction of resolution conversions from RGB to YUV. First, we are changing the color space from RGB to YUV or YCB CR. Then motion estimation and compensation. Then DCT quantization and entropy code. Today we are going to discuss this first two steps. Then next week we are going to discuss this one. Right? Because this is a bit complicated. Then after this lecture, you can go through again the lecture notes and get the best idea about these two topics, these two steps. Then finally, we can look into this step by next week, right? Therefore, I will share these notes with you after this lecture. Then you can go through these first two steps and get a better idea, right? Then we can discuss this one. Right. Why we are converting RGB to YUV or YCB CR? I mentioned in the color space lecture, RGB is mainly considered in the just color, just only consider the color. But YUV or YCB CR, what is mean by Y? but it's give the Y and C UVO CBCR. Y channel is responsible for the luminance of the image, luminance or the lightness of the image. U, V, O, C, B, O, C, R is responsible for color information, information about the color, right? Y channel is responsible for the luminance or the lightness of the image or a video, right? That is the reason. Here, see, this is a low luminance and this is the high luminance. The second one is the more attractive, right? This is more eye-catching. But if first one is having low luminance, when the first image randomly let's say we are randomly see on these two images, this one is the most eye-catching one, right? Because it has high luminance, right? Then when we are considering or when we are doing the video compression, we have to uh, consider the luminance as well, right? In RGB, just only consider the color, but YUE or YCBCR color spaces, they are considering or responsible responsible for the luminance of the image or a video, and CBCR or UV are considering the color space, the information about the color. Then we can get UV part separately and perform the compression instead of considering all three channels, right? That is the importance of conversion from RGB to YUV color space. The first step, conversion, RGB to YUV. Then we can perform chromium subsampling. Chromium subsampling means we are reducing the color pixels, right? We are reducing the color pixels. In the first row, it gives the ratio 4 by 4 by 4. In here, this is the Y. This one is the UNB, right? Y gives the luminance of the or the lightness of the video. UV and U and V channels gives the information about the color, right? We are separate first. We can separate. Then we are reducing the number of pixels according to this ratio. In first row, it gives 4 by 4 by 4. It means not reducing the number of pixels. This is the input for considering pixels, then not reducing 4 by 4 by 4, or simply 1 by 1 by 1, not removing pixels, right? You can see as the result, this is the result, not reducing the number of pixels. But in second row, it 4 by 2 by 2. It's considering 4 pixels. Out of 4, it reduced to half. See, for this 4, this 2, it gives 1. For this 2, it gives another 1. For this one, it gives 1. It gives, for this one, it gives 1. Totally, this one has 8 pixels, but now we have 4 pixels. It reduced to half, right? That is in this ratio. When we using this ratio, it reduces 8 pixel into 4 pixels into half. Then adding luma or the luminance and the chroma and the color information, we can get this result. When we get 4 by 2 by 0, see, for this color, these 2 pixels, it gives just only 1 pixel. For these 2 pixels, it gives another 1 pixel. And with combining luma, we can get this result, right? Here we are chroma subsampling or chromium subsampling means removing number of pixels. For this one, for this example, it gives different colors for understanding, but in real world scenario, uh, most of the cases, these pixels are almost same, right? For this image as well, you can see when we, let's say, when we consider this area, when we consider this area for chromium subsampling, you can see all the pixels are at the same color, right? Almost same color. Then we can remove unwanted pixel and come up with this number of pixels. This number of pixels. That is how important of chromium subsampling. For this image, this slide, it used different or 8 different colors for the understanding, but in real world case, it will not make a huge difference in this area, right? But in this case, you can see a huge difference in the original one and the resulted one. But in this type of cases, it not gives a huge difference with the original one and the compression one, right? This is the chromium subsampling. Right. Right. Then the second one, motion estimation. First part, conversion, color space conversion, RBG to YUV or YCB CR. Why we convert RCB from RB to RCB to YCB CR? The most important factor of a video or an image is the luminance of the image, right? Then we have to consider luminance and the color factor as well. Then we can separate luminance or the lightness of the image or a video and the color information by using YCBCRO YUV color space. That is the reason why we are changing or convert R from RCB to YCB CRO YUV color space. Then motion estimation. Motion estimation means we are identifying similar blocks, similar macro blocks among uh, the pixels, right? In this case, we can consider iframe or p frame or b frames, right? Iframes mean intra coding, p and b are inter-frame coding, right? P frame is called predicted, b frame is called bidirectional, right? P frame considering the previous frame as the reference frame, B frame considering previous frame and the next frame as the reference frame for identifying the macro blocks, right? In motion estimation, we have 5 steps. Frame segmentation means we can divide our frame into small parts or simply macro blocks or the blocks, right? We call it as frame segmentation. Then search threshold. We can search similar pixels with the reference frame. It's called search threshold. Then block matching. After searching, we can identify uh, similar blocks. Then prediction error coding. In video compression, we it could be have some errors as well. Then we have to consider the error as error correction as well. Then we have to consider the prediction error coding as well. Finally, we are calculating the motion vector. Motion vector. This motion vector and the prediction error coding part will be discussed by next week, right? First, frame segmentation, search threshold, and block matching. These 3 topics are we are going to discuss in this session, right? Motion estimation. Motion estimation means I mentioned earlier, we are considering reference frame and the target frame and find out the matching blocks, right? Matching blocks. For this this purpose, we can use these 4 techniques: block matching algorithm, phase correlation and frequency domain methods, pixel recursive algorithm, and optical flow. This optical flow is widely used nowadays because it's using AI or machine learning techniques. Therefore, I'm going to consider this one. For this lecture, we are going to look at block matching algorithm. Only block matching algorithm, right? Using this algorithm, we are going to find out the matching blocks among reference frame and the target frame. It is called motion estimation, right? Then motion compensation. It means calculating the motion vector, how amount of changes that are happening in reference frame and the target frame, right? There are 2 types of compensations: forward compensation and backward compensation. For the forward compensation, uh, coding current frame using the previous frame, we called it as forward compensation, right? We are considering this frame as the target frame and the reference frame as the previous one. We call this one as forward compensation. Backward compensation means we are considering the coding current frame and taking the next frame as the reference frame. This one is the backward compensation. This one is backward. This one is forward. Right? For the coding purpose, we are considering the previous one as the reference frame. We call this it as forward compensation, and we are considering the next frame for coding to the current frame. We call it as backward compensation. You have to keep in mind those words as well, right? Motion estimation, compensation, forward compensation, backward compensation, others, block matching algorithms, and this frame segmentation, search threshold, block matching, right? You have to remind those words, right? Then types of motion and reasons for difference, right? When we see a video, uh, we can see some difference between one frame to another frame. In this slide, we are going to discuss why these changes are happened for the video, right? There are a few reasons, right? First one is camera motion. In some kind of videos, some kind of films, sometimes camera is more moving, but object is still. Object is in a static place, static location. Camera is moving. Then, due to this reason, we can identify some differences with the frames, right? Camera is moving, but object is still. For an example, see this video. Yeah. See this one. See, the objects are still. These objects are not changing time to time, but camera is moving. Then we can identify some differences, right? But here also, the object is not moving. Sorry. Here, object is not moving, but camera is moving. Then we can identify some differences, right? Then object is moving, but camera is still. Sometimes object will be moved. Let's see, you are capturing a car race, right? Then you can uh, keep your camera steady, but cars are moving. Then objects are moving, but camera is steady. Then again, you can identify some different or the difference among the frames. Then Another one is illumination, changes of sun rising or headlights, right? Sometimes you can capture a car, right? Capture the car is in steady, and also the camera is in a static position, steady, but suddenly uh, the lights are on of the car, right? Then you can identify some differences. Again, the sun rising as well, right? Uh, Depending on the sun, the light, amount of light, we can identify the differences among the frames. Then scene and cuts. I have showed you an example in the previous during a previous case, a previous lecture. We can add some effects, right? We can put some effect to in between two frames, right? We can add some effect in between two frames. I have used a effect to when we changing one frame to another frame, I add a effect with it getting darker and change to another frame. It getting gradually getting darker and change to another frame. Again, we can identify some differences, huge differences in between two different frames. Then noises. Some images can have some noises, right? Unwanted colors, unwanted effects. Then again, we can identify some differences among frames, right? Those are the reasons we can identify differences in between two frames or more than one frame. First one is or the single frame itself as well, right? When we move a camera, but the object is steady, we can identify some differences among the frames, right? Camera motion, due to camera motion, due to object motion, and both as well. Sometimes camera is more moving as well as the objects are again moving. Both are moving, then again we can identify some difference. Then the illumination changes, scene cuts, and noises. Those are the few factors uh, for difference. We can identify differences in between one frame to another frame. Okay. Then motion estimation. Motion estimation, I mentioned earlier, motion estimation means identifying the difference blocks among two different frames, right? Okay, let's take this one, right side as the portion of interest. We are going to we are going to identify similar pixels in this area. This is the current frame. And the previous frame we are considering as the reference frame. Here we are going to use P frames, right? P frame. This one is the current frame, and considering previous frame as the reference frame, here we are going to use the concept of P frame, right? This is the portion of interest. Then we have to mark the search window, right? We are going to look at similar pixels in this area, right? Actually, this is just not a flower. Let's say this is the flower, right? This is the blocks or the pixels. It is not exact flower. We have some pixels values, right? 0 to 255 values. Here also we have set of pixels and the pixel values, right? Then we can compare this pixel with this pixel, this pixel with this pixel in general, right? We are not going to compare pixel by pixel. We are comparing the blocks, right? Blocks has 8 by 8 pixels, then totally 64-bit pixels at once. A single comparison, we are going to check 64 pixels, right? But in general, for the understanding, we can consider this one, right? We are comparing one pixel to the respect to another pixel, right? Then we can identify the similar pixels. We call this one as motion estimation, right? Then this is in general, but in real world case, we are going to compare blocks, block-based motion estimation. We are not comparing pixel by pixel. We are comparing block by block, right? This one is the current frame. This is the reference frame. Then we can consider a block. We can consider a block and a block from the reference frame as well. Then we can identify the similarities among this reference frame and current frame. The standard macro block size is 16 by 16. This is the standard one. I showed you in the previous slide. Macro block has 4 blocks. This one block has 8 by 8 pixels. It means 8 pixels, 8 pixels, 8 pixels, 8 pixels. Totally 16 pixels for this side, 16 pixels for this side. Totally this amount of pixels that are considering for a single comparison. The standard macro block size is 16 by 16. Using these macro blocks, we can identify similarities among reference frame and the target current frame in this way. We can consider or we can identify the pixel values, right, by taking macro blocks, right? Then okay, this is the way we can calculate the motion vector using identified similar macro blocks, right? How amount of changes that are happening among reference frame with target frame. We can continue the rest by next week, right? Up to now we have discussed about the up to motion estimation, right? In the motion estimation we have to consider macro blocks to compare reference frame and the target frame, right? When I go back to this point, we have 3 different ways to identify the similarities among frames: I frame, P frame, and B frame. In I frame, we are just only considering single frame to identify similar areas, similar blocks, similar macro blocks, right? In the P frame, we are considering previous frame as the reference frame for the current frame at the, to compare for the comparison. Then B frame, we are considering previous frame and the next frame as the reference frame. Then this is the best one for video compression. Then I told you here in P frames, first one is definitely an I frame because we no more frames to get the reference for this one. Therefore, the first one is definitely an I frame. Then another one. Next one could be some P frames or B frames. In B frames, we can consider both previous and next frames as the reference frame. Then these are the very important steps of MPEG compression. First, we have to convert color space from RGB to YUV or YCB CR color space. What is the reason? The luminance or the lightness of the video or the image is the important one for video compression. We have to consider the luminance of the video and the color. We can consider the color space for the video compression when we're using YCBO, YCBCR or YUV color space, because the Y channel is responsible for the luminance, and UV and CBCR channels are responsible with the color information. But in RGB, just only we have R, red, green, and blue channels. R channel is responsible with red, G channel is responsible with green, B channel is responsible with blue, right? We don't have a separate channel for the luminance here. but in this case we have a separate channel. We can separate this luminance channel and the color channel separately, and we can perform some comparison on UV or CBCR channel. Then motion estimation and compensation, then TCT quantization and entropy coding. Then the color comparison. Then this is the chromium subsampling. We can separate the luminance part, luma as the separate one, and the chrominance part separately. This is Y channel, and this UV or CBCR color channels. Then according to this ratio, we can reduce the number of pixels, right? When we're using 4 by 2 by 2, it will reduce the number of pixels into half. This original channel, it has 8 different pixels, but in this case we have 4 different pixels, reduced to half. Then we can add again this luma and the chroma. Here we can notice that luma is not changing. When we compressing, luma is not changing, but we are changing the number of pixels in chroma, right? Then when we using 4 by 2 by 0, it further reduce the number of pixel into quarter, right? Totally now we have 2 different pixels. Then we can add luma and chroma, and finally we can get this result, right? Then motion estimation. Again, we can consider iframes, keyframes, or D-frames for the video compression. We have 5 main steps for motion estimation. First, frame segmentation, or we can get this small parts. For the comparison, we call it as frame segmentation, right? Then search threshold. We can search with the current frame and the previous frame or the reference frames. Then block matching. We can match the similarities among the frames. Then prediction error coding, and finally we can calculate the motion vector, right? We can discuss about the prediction error coding and motion vector by next week. Then motion estimation means find out the similar macro blocks. Here we are going to consider this algorithm, block matching algorithm, right? Then motion compensation means calculate the amount or the motion vector by considering this information taken from motion estimation, right? By using this information, we can do the motion compensation. We have 2 different types for the motion compensation: forward compensation and backward compensation. In forward compensation, we are considering the previous frame as the reference frame for the forward compensation. In backward compensation, we are using next frame as the reference frame for current frame compensation. And this is the different types of motions that are subjected to make some changes among the frames. First one is camera motion. The object is still, but camera is moving. Then we can see some differences among the 2 frames, 2 or more frames, right? The second one is object motion. The object is moving, camera is still, right? Object is moving, camera is still. Again, we can see some, or we can identify some differences among the 2 frames, right? And both are moving. Camera is moving, and also objects are moving. Again, we can see some differences in the and the illumination changes, and scene cuts also make some changes among the different frames. And the next one is noises. Some unwanted colors can be added due to some bad color, bad light conditions, bad camera quality, bad or some unwanted pixels can be added to our video or an image. Then we call those as noises. Right, then motion estimation in general. I told you we are comparing one part to another part. Simply we can say one pixel to another pixel. Then we can identify the pixels. Before identifying the pixels, before comparing the pixel, we have to uh, uh, say this is the portion or this is the area we are going to check in the current frame. So we have to initialize the portion of interest in the current frame, and also we have to initialize the reference frame, or we call this one as region of interest, right? This is the search window. This is the search window. This is the region of interest, right? Before starting the comparison, we have to initialize those two parameters, region of interest and the search window. After that, we can search, or we can compare block by block, or simply pixel by pixel, and identify the similarities among current frame and the reference frame. In real world case, we are considering the macro blocks, not the pixel. It just only considering the blocks, block by blocks, not considering the pixel by pixel. After find out the or the block size should be in macro block size should be in 16 by 16 size, right? After find out the similarities among the two different frames, we can identify the we can calculate the motion vector, right? I will stop from this point. Video compression, right? There are three main steps that are involving with video compression. The first one is reduction of resolution conversion from RGB to YCBCR or UV. In other words, first of all, we have to convert our video into or the frame into RGB, from RGB to YUV or YCBCR color space. Then motion estimation and compensation. Then finally DCT. Actually, these are some algorithms, right? DCT, quantization, and entropy coding. All right. We have discussed up to this point. This point, right? As I told you in the last time, for the motion estimation, or find out the motion vector, we have to take a current frame as well as the reference frame, right? This one will taken as the current frame, and this one will be the reference frame. And you can see there's a area is highlighted on the right hand side image, this one, right? Then we are predicting, right? This purple color square shows the predicted area, or the most matching area, right, to this blue color one, right? As you can see, there are some motion that are happening in the cloud, right? Upward direction and left side, right? Then you can see there are some differences in between current frame and reference frame. You can see this is the location where the object or this image is available in the current frame, but in previous or the reference frame, this area is the matching area for this selected area, or we can say this one is the matching block, right? Matching block. Then you can see there are some displacement, right? In the motion vector, we are going to calculate this part. This is the motion vector, right? How amount of changes that are happening in between reference frame and the current frame, right? In motion vector, we are going to find out these changes, right? How amount is changed in between reference frames and the current frame, right? This is another example for predicted blocks, right? This is the current frame. This is the current frame. This is the reference frame, right? This the matching block for this block number 1 is this one in the predicted or the reference frame, right? And for the block number 7 in the current frame, this one is the matching block in the reference frame, right? And so on, we can find out in this image, we can find out the matching block in the reference frame. We call these matching blocks are predicted blocks, predicted blocks. And please note that you can see there are some changes. Let's say this is XY coordinate system, right? X and Y, this is the origin. Then you can see there are some displacement. Let's say this is the origin of this point 0, 0, and in the predicted blocks the origin coordinate of this origin will be changes, right? You can see there are some movement available in this first block, right? Let's say this one is 1, 0. The location is changed, right? Therefore you can see in the predicted blocks, you can see there are some changes that are happening in the there are some movement or relative movement that there are available in between current frame and the reference frame. We call these types of predictions, we call these in this word, using this word, predicted blocks. Those are some predicted blocks, right? Then there are some algorithms that are available to calculate this motion vector. First one is mean absolute difference. Second one is mean square difference, right? We can use both of these algorithms to calculate the motion vector, but the second one is most efficient, right? You can see in this second one, we are considering the mean square value, mean square difference, right? But in this case, we are just calculating or get the intensity or the pixel value, right? Difference of pixel value, reference frame and the current frame. But in this case, we are getting the difference in between pixel values in between reference frame and the current frame. Then we are calculating the square value and add those things and divide by number of pixels, right? This one will give more accurate result. Therefore, frequently using this second one, right? Mean square difference. Just remember there are two different measures, two different algorithms that are available to calculate the motion estimation or the motion vector. And the second one is the most suitable one. First one is using, but second one is giving a better result for motion calculation, right? Let's take an example and see how we can calculate the motion vector, right? Before moving to this part, I will show you an example. Okay. Okay, let's take an example. Let's say this is your image. This is the reference frame, right? This is the reference frame. Right? We have some pixel values. In real world scenario, we are not calculating pixel by pixel. It will consider block by block, right? But for simplification or the understanding, I'm going to consider pixel by pixel, right? Let's say this is the pixel values of the reference frame. There are some 16 pixels are there. These are the pixel values. there are some, these are some random values, right? Not the fixed values, there are some random values. Let's say eight, five, 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 two, four, right? This is the reference frame. Then this is the current frame or the target frame. Some pixels are there available in this one as well. And so on, right? And for this example, I'm going to consider this block as the macro block. This is the area we are going to find the matching area from reference frame. This one will be taken as the macro block, right? Macro block. In real world scenario, we are getting the 16 by 16 macro blocks. It means 16 pixel for this side and 16 pixel for this side, totally 256 pixels for a macro block. But in this example, I'm going to consider 2 by 2 macro block, right? Then we have to calculate the differences. It means, let's say this block is placed on top of this reference frame, right? This block is placed on top of this reference frame. Then we can apply this algorithm, right? This one. Right? We can say 1 minus 6 pixel value from reference frame subtract by pixel value of current frame. Then calculate the square value plus 4 minus 4 squared plus 2 minus 2 squared plus 5 minus 2 squared, then divided by 1, 2, 3, 4 pixels, right? If you get the standard macro block, you have to divide this by 256 because we are considering 256 pixels for a single macro block, right? Then this one will give 1 minus 6 means 5, 5 times 5, 25 plus 0 plus 0 plus 3 times 3, so 3 to the power 2, 9. Then divide by 4. Then 25 plus 9, 34. Divide by 4. It is around 8, so 8.5. Right? This is the calculated motion vector for this block. Right? For this block. Then this is for this block. Then we have to consider the second part, this one. We are placing this macro block with this one, right? The second one. This is the first one. This is the second one. Again, we have to calculate the motion vector with these two frames for a set of pixels, right? I'll just remove this calculation. Going fine. And for the first one, it is given 8.5. First one, 8.5, right? For the second one, let's try to calculate this motion vector for the second one, or the mean square difference for the second one. Four minus 6 squared plus, right, this one with this one. 4 minus 6 squared plus 6 minus 4 squared plus 5 minus 2 squared plus 3 minus 2, then divided by 4. 4 minus 6 minus 2 minus 2 to the power minus 2 plus 4. 6 minus 4 again 2 to the power 2 again 4. 5 minus 2 3, 2 to the power 3 9, and for this one 1 divided by 4. 4 8 8 plus 9 17, 17 plus 1 18, divided by 4. We will get 4.5 for the second one. Then something similar to this one, we are placing this macro block on top of this frame, third, fourth, fifth, and so on. We are getting 9 different values, right? First one, second one, third one, fourth, fifth, sixth, seventh, eighth, and 9. There are 9 values we are going to calculate, right? Out of these 9 values, we are getting the smallest one. We are getting the smallest one. Let's assume this is the smallest one for this scenario, right? This one, the purple color, this block is the smallest one for this example, right? This is the smallest one we are getting by calculating the mean square difference for this scenario. For an example, right? This one. Which one? First one, second one, third one, fourth, and fifth one, right? For an example, you can write down these values on a piece of paper and just try to calculate what is the smallest one. Probably this one will give this smallest one out of this means 9 means star difference values, right? Let's say this one is the shortest one, smallest one, or the smallest mean star difference of this calculation, right? But it means this is the most matching block in between current frame and the reference frame. In other words, this one, the purple color one in the left side, is the most matching block, matching pixels for this macro block, right? Then we are consider this matching block and the target block for the macro block. Okay, I will remove this part from this side. Right, and take this matching block and the target block. This is the matching block. These are the pixels, pixel values 5, 3, 2, 4. This is the matching block from reference frame. This is the target block or the macro block. 6, 4, 2, 2. This is the target block, right? Then we subtract from matching block with the target block, right? We are subtracting matching block from target block. 5 minus 6 means minus 1, right? Then 3 minus 4 means again minus 1. 2 minus 2, 0. 4 minus 2, 2, right? We called this one as the prediction error. Right? These are the changes that are available in these pixels. Right? Currently, this pixel have value 6, but previously it has 5. Currently, this pixel has 4. Previously, it had 3. Right? Then we are getting the prediction error, or we call this one as difference image. Difference image. Right? After find out the difference image, we can apply other algorithms. Let's say JPEG compression, right? We can apply other steps for this one. First, convert color model, then apply DCT and RLE algorithms on top of this difference image, right? Okay, let's try to calculate the motion vector from this for these blocks, right? Let's assume this is the origin of this system. Prediction error. I hope you asked about this one, right? This one, prediction error. Prediction error. Or we call this one as difference image. Right. Let's assume this is the origin of this frames. Then coordinates will be 0, 0. Again, this one also, this is the origin, 0, 0. Right? Let's take the starting point of this matching block. It is 0, 0. Right? Then what is the coordinate? Sorry, not 0, 0. Move to right side and the down side. Then the coordinate of this point will be 1, 1. Right? I hope this is clear. Let's say this is the XY coordinate system. Right? This is the origin. Then the coordinate of this point will be 1, 1. Right? Coordinate of this point is 1, 1 for the target frame or the matching block. Then for the macro block or the let's say this target frame, this is the coordinate for the target frame 0, 0. This is matching block. This is the target frame. Right? 1, 1. This is the coordinate of this point, and this is the coordinate of macro block. Then we are getting the difference of this macro block and target frame. We are calculating the or we are subtracting from matching block with target frame. Then 1 minus 0 is 1. 1 minus 0 again 1. This is the calculated motion vector of this scenario. You can see this block is move in this direction. I'm using this color, right? This block is moved in this direction, right? This one is the most matching one for this target frame or the macro block. Then you can see this macro block or the target frame or this set of pixels are moving in this direction, right? Previously, it is available in this location in the previous frame, but in the current frame, this frame is moved in this direction, right? This is the amount that are displays of this target or the matching block, right? This is the amount that are changed from target frame and the reference frame, right? Let's assume this is the matching block for this one. This is the matching block for this considered one, right? This is the matching block for this one. Then this is the coordinates of this block, which is 2, 2, right? From the previous frame. In the current frame, this is the place our macro block is available. Again, the origin of this macro block is 0, 0. Then for this second scenario, we can reduce or we can subtract 2, 2, 0, 0, right? From matching block to target block, right? Again, we can get a result 2, 2, because 2 minus 0, 2, 2 minus 0, again 2. Then this one will give the amount of changes that are happening for this considered block. Previously, it is available in this location, but in current frame, it is available in this location. This amount is changed, right? This amount is changed. This amount of changes that are available with comparing matching block target frame and the reference frame. Then this is we call motion vector, right? Then we are using this motion vector for the further calculations, right? Okay, then we can move to the next part. Okay, there are 3 algorithms we have to find out these matching blocks, right? For this motion vector calculation, we have 3 different algorithms. First one is full search, second one is 3-step search, third one is 2D logarithmic search. In full search, we are comparing all pixels as we did in this example. For this example, we have to calculate 9 different mean square values because we are placing our macro block on the pixels on the reference frame. Again, move to the next set of pixels. Again, move to the next set of pixels, and so on. We have to calculate 9 different mean square values, right? But we call this one as full search. This one will give good accuracy because we are searching entire image, entire frame, but the time consumed, it is very time consuming and large amount of computational power is needed, right? For this one, we are only consider 16 pixels. Then we have 9 different values, right? Let's say if you get 256 pixels at a time, let's say a 16 by 16 macro block, you have to calculate more and more calculations. Then it will need a large amount of computational power and as well as the it is very time consuming. Therefore, this one will give a good accuracy results, but it is not good for large scale of projects, right? And the second one, block matching algorithm. This is quite fast with compared to the previous one. First one is 3-step search. It is an algorithm, right? these steps should be followed to complete this task, right? There are 8 steps. First, start with search location at the center. Yeah, find out the center of this frame. Then select an initial step size. For this one, s equals 4. Step size is 4. For this step size, we are getting the multiples of 2. 2, 4, 8, then 16, and so on. Those values are getting at the initial step. For this example, 4. Then search 8 locations, pixels around location 0, 0. 0, 0 means origin and the 0, 0, right? Let's say for this example, this one is the origin. This one is the origin. And according to this initial or initialized step size, we are find out other 8 pixels. See, this pixel is available from this one with 8 units, 4 units, right? Because the initial step size is 4. 1, 2, 3, 4, and so on. We are calculating or we are finding other 8 different pixels, 8 different blocks, 8 blocks with respect to this selected origin, right? In this case, we are considering the diagonal sides as well, right? Then after that, we are calculating the actually this one is a bit complicated. Let's say we are that just remember we are applying a function, right? We call it as cost function, right? Cost function. We are applying cost function in between this origin and other selected points, right? We are applying cost function, right? We are applying cost function in between this origin and other selected points. Then select the least amount of cost value in between this origin and out of these 8 pixels. Let's assume this one give the least amount of cost value in between this origin and this point, right? Then this one will be the new origin for upcoming steps, right? This one will be the new origin, right? Then change our step size to s equals s divided by 2. Previously s is 4, then s divided by 2 means 2. Then step size is 2. Cost function is a bit it is let's say okay, I will show you an with an example on next day, right? For the cost function, right? It is bit harder to understand. I will show you an example with an example by next day, right? Only just assume you are applying a cost function and find out the least amount in between this origin and the this out of this pixels, right? Points. Then this one will be the next origin of our searching algorithm. Then apply or calculate the new step size, right? Previously it is 4, then s divided by 4. 4 divided by 2, it means 2. Then find out again another set of points, 8 points. Again, we are applying cost function, right? Then assume this one will give the least amount for the cost function, right? Then this point will be another or the next origin for the searching algorithm, right? Then again, calculate the new step size. Currently, S is 2, 2 divided by 2, it is 1. Then based on this step size, again we have to find out another 8 points with respect to the new origin, right? Again we are applying a cost function in between new origin and these 8 points and find out the least cost value given from this third step. Then finally, if the S is 1, we are getting the result, right? We are getting the cost value from first origin point and the last point. For this example, this is the first origin point. This is the last point we found, which is given the least cost value. Then we are calculating cost value in between this point and this point, right? This is how we can apply this algorithm in block matching, right? This is three-step search. We called it as 3SS as well, right? Next one is 2D logarithmic search. It has 8 steps, right? In this case, we are considering 4 points instead of considering the 8 points, right? Just only 4 points, not consider the diagonal sides. Again, we have to initialize a step value. In this case, it is s equals 8, right? Then search for 4 locations at a distance of s from center on the x and y axis, right? 4 different values. Then find the location of the point with least cost function. Again, we are finding the least cost value, applying cost function. Then let's assume this one is the point which is giving the least cost value. Then this one will consider the new center, right? New center and step repeating step 2 and 3, right? And as the sixth step, if the best matching point is at the center, then we update our step size with s equals s divided by 2, like previous, right? For this one, we are not changing the step size, right? And applying steps 2 and 3. Again, let's assume this one will give the least cost value. Again, this one will consider the new center or the origin of this searching algorithm. Again, we are getting this and these points as the next 4 points, because these points are all already considered. Therefore, only we have to consider this point and this point. Then let's assume this one will give the least point, right? Then we are reducing, or we are calculating new step size. S divided by 2, it means 4, right? Then based on this, we are getting values, right? We are calculating the cost value. Then we have to calculate the least cost value given from this new set of points. Then if s equals 1, all 8 locations should be considered. In previous case, from the beginning, we have to consider all 8 points. But in this case, if s equals 1, we have to consider 8 locations. For the previous step, or the previous step size values, we are only considered 4 points, right? That is a difference of of previous one and this one. Then finally, we have to calculate the minimum cost function given in between last found point and the previous one, for the first origin, right? This is the 2D logarithmic search. We will discuss with this one again in your tutorial sessions as well. I will give you some questions based on this these two algorithms, and we can discuss further about this algorithms, right? This is again an example of a 2D logarithmic search algorithm. This is the least cost value given from this point. Then this one will be the new origin and consider these 3 points. And let's assume this one will give the least cost value, right? Then these 2 points should be considered with this previous origin or the new origin, and this one will give the least amount. Then we have to consider this one, all points. We don't have any points in this side, therefore only we have to consider these 5 points. Then assume this one will give the least cost value. Then calculate the cost value in between first origin and the last point, last found point, right? This is the 2D logarithmic search algorithm. Okay, then we can discuss this one, motion compensation. This is an example with some real world image, right? This one will taken as the previous image for the reference frame. This one will be the current frame. Then see these differences. You can see there are some differences available in these both frames, right? The camera is moving or the character is changing their facial expressions, right? There are some differences. Then we are partition of the frame 2. It means we are divide our frames into blocks. This is a block, right? Then we are comparing this block for the current frame and the reference frame and find out the most matching regions available in the reference frame, like this one. Like this one, right? This one. As you can see in this example, there are some matching areas or predicted areas available in the reference frame. Then we are calculating the motion vector. See, in this image, it gives some arrow marks. It means with compare with the reference frame and the current frame, this amount of or this direction, this set of pixels are moving, right? This set of pixels are moving in this direction. This set of pixels are moving in this direction with compared to reference frame and the current frame. We call this one as displacement vector or the motion vector, right? Finally, we are getting the difference in between reference frame and the current frame. And finally, we are come up with the difference image, right? We can reduce this one from this one, right? This gray color pixels are given, the gray color pixels are almost similar, but in this with light images or light blocks, these are the changed pixels, right? These 4 pixels are not changing, therefore it is given some amount of gray color. But in this set of pixels are given some light areas. In these blocks, it means these pixels are changed with compared to current frame and the previous frame. Right. After calculating the motion vector for the difference image, we can apply the algorithm for compression. Right. This is the previous frame. This is the current frame. Right. Then we can get the changes or the similarities in between these frames. Then we can come up with the difference image. Right. Then if we calculate the motion vector, we can directly apply it to Huffman coding and we can compress our video, or we can apply JPEG algorithms, JPEG compression algorithm to compression as well, right? We can directly apply motion vector to Huffman coding and get the compressed one, or we can apply this DCT quantization and RLE algorithm. DCT means discrete cosine transformation, then quantization and runner length encoding, right? Runner length encoding. DCT means discrete cosine transformation. DCT means discrete cosine transformation. RLE means runner length encoding, right? These are the algorithms we are applying for this difference image when we consider the JPEG compression algorithm. In another way, we can, if you calculate the motion vector, we can apply it to Huffman coding and come up with the compressed one. We are discussing about these three algorithms in deep in the image compression, right? Within next 2 weeks, we are going to discuss about the image compression. In the image compression, we are going to discuss further about this DCT quantization and RLE algorithms. For just now, just remember, after calculating the difference or after find out the difference image, we can apply DCT quantization and RLE algorithms, and finally we are applying Huffman coding to compress our frames, right? This is the complete path of MPEG-1 compression, right? We are discussed up to this point in detail, right? Right now, up to this point, for these steps, we are discussed during the image compression sessions, right? Okay, we can move to the next one. You already know these things: I frame, B frame, and P frame, right? When we get the set of frames from the sequence of frames in the our video, we called it as this slide. I can discuss. I hope you have remembered those things, right? This is group of pictures. Out of group of pictures, we are getting the picture, then slice, macro block, and a macro block has 4 different pixels, or 4 different blocks. Blocks contains 8 by 8 pixels. It means 16 pixels, right? Right? Then we are considering some frames, right? For for the comparison, for iframes, we are not getting any reference frame out reference frame. We are search the matching pixels by itself, right? It is only consider a single frame and find out the similar areas. In P frames, we are getting the previous frame as the reference frame and consider the current frame and compare both frames. In B frames or bidirectional frames, we are considering previous frame and the next frame as the reference frame and compare or find out the matching areas in between previous frame and the in between current frame with the previous frame and the next frame, right? In B frames, right? For this comparison, we are only compare iframe with itself, right? We are not no need to think about the iframe because it is only consider the content of itself and find out the similar areas. But in P frame, we have to get the previous frame as the reference frame, right? For this case, we are only taking I frames as the previous frame, right? I frame as the previous frame for P frames. For P frames, for P frames, we are getting I frames as reference frame, right? For B frames, we can get I frame and P frames as reference frame, right? Before the comparison, before find out the matching areas, we have to consider, let's say this is the input stream, then we have to consider these are taken as B frame, these are taken as P frames, these are taken as I frames. We have to consider those things, right? In compression, the algorithms are automatically select those are the selected B frames, those are selected I frames, those are the selected P frames. After that, we have to compress this stream, right? Let's say this is a P frame, then we have to take a previous frame as the reference frame, and there is a condition for the P frames. We are only getting a reference frame as the I frame. Then we have to get this one as the reference frame for this P frame, right? For B frames, we can get both P frames and I frames as the reference frame. Then for this one, for this frame, this one will be the previous frame and this one will be the next frame. We cannot get this one as the reference frame for this B frame because we are not getting B frames as the reference frame for B frames, right? Okay, I will show you with this. Let's say these are the set of frames given. First one should be an I frame, right? First one should be an I frame, then B frame, B frame, P frame, B frame, P frame, and I frame. I frames we don't take in a reference frame, then we don't no need to consider. But let's say this one will be the current frame, then we have to get a reference frame as the previous frame, right? Then we have to take this one as the reference frame for this P frame, right? And for this B frame, we cannot get the B frame as the reference frame for this one. Therefore, we have to get this I frame as the reference frame for this B and this one, because we can get I frame and P frame for B frames as the reference frames. For this one, again we cannot take B frame as a reference frame for this B frame. Therefore, this one will be the next reference frame for this one, and this one will be the previous reference frame for previous one, right? For this B frame, we can get this P frame as the reference frame for previous one, and this I frame as the reference frame for next one. We cannot take this one as the reference frame. We cannot take this one because B frames are not reference to B another B frame, right? Then we then we have to rearrange those things, rearrange these frames according to these predictions, right? I will discuss about that one from this one, right? This slide. Okay. Then just remember for this point, we are not taking B frames as the reference frame for another B frame. We are just only consider I frame and P frame for reference frames for the B frames. Then for the P frames, I frames or only I frames will be the reference frame, right? Okay, then these are the steps that are take place in interframe coding first, because we are not getting a reference frame for the comparison. We are only find out the similar areas, so matching areas itself in intraframe or iframes, right? First, we are converting RGB to YUV or YCBCR, then divide our frame into macro blocks, then find out the matching blocks, then apply DCT algorithm, quantization, and entropy coding, right? These are the steps for iframe, but in P frames, it is very bit different, because P frame we are getting reference frame and the target frame. We are considering two frames, then we are getting the difference in macro block or difference image, as we did in previous example, right? Getting the find out the difference image, we can then convert it to the color space, right? First, we are getting the difference image, then convert color space from RGB to YCBCR. Then we can apply DCT, quantization, and entropy coding, and finally we can get the we can apply Huffman coding, right? Or in other words, we after find out the matching block, we can get the motion vector. Then we can directly apply motion vectors to the data about the motion vector to the entropy coding, right? This is the P frame encoding. P frame encoding, right? We are considering target frame and reference frame. Out of this target frame and reference frame, we can get the difference image or difference macro block, or we call it as prediction error, right? After this, find out the difference image, we are converting the color space from RGB to YCBCR or YUV. After that, we can apply DCT, quantization, and entropy coding. Or in other way, if we find out the matching block in between target frame and reference frame, we can get the motion vector. After that, we can directly apply this entropy coding. Sorry, after we can apply what we call this one. I just remember Huffman coding, right? After we can directly apply Huffman coding for motion vector. This is the story of P frames. In B frames is bit different. In B frames is bit different because we are getting two reference frames, right? Previous frame and the next frame will be the reference frame for this target frame, right? Then we have to get the average value from this one and this one, previous frame and the next frame, right? In this case, we are only just considering one frame as the reference frame and this one is the target frame, and we can just directly calculate the difference image, right? But in this case, we have to consider two different matching areas because we are getting two reference frames. Therefore, we have to calculate the average of this frame from this frame and this frame. And same as before, we can reduce or we can find out the difference image with reducing target from target frame with the calculated or finded average frame, right? In this case, it's a bit different. We cannot directly apply this selected frame or target frame, selected frame from this reference frame, because we have two selected frames, right? We have two selected frames. Then we have to find out, or we have to calculate the average of this previous frame and the reference frame. Then we can reduce it from target frame, and we can apply again the previous steps, right? We can follow the previous steps. After find out the difference block, difference macro block, or difference image, we can apply color transformation, RGB to ICB-CRO, YUV color space. Then we can apply DCT, quantization and entropy coding, and finally we can apply Huffman code. Or in other way, in this case, we have two motion vectors. In previous case, we have just only one motion vector, but in this case, we have two motion vectors, because this from this one and this one. You can see currently this area is available in this position. It is previously available in this position and this position. There are some movements are there in this selected area. Then we have to have two motion vectors. After that, find out these two motion vectors, we can apply Huffman coding for compression purpose, right? The main difference in between P frame and B frame is this one. We have to calculate the average from this previous frame and reference frame. This is the only difference with compared to B frames and I frames, right? Okay, this one is the previous one. I told you iframes get the reference frame itself to find out the matching areas. For B frames, we have to get the I frame and the P frame as the reference frame. In P frames, we cannot get, for the P frames, we cannot get another P frames for reference frame. Only we are considering I frames as the reference frame for P frames. Therefore, we have to reorder those frames. Reorder those frames, right? For this example, let's say this I frame is taken the same frame as the reference frame, right? For this B frame, let's say, oh yeah, for this B frame, we can take this one as the reference frame for previous frame, and we cannot get another B frame for frame as the reference frame for this B frame. Then we have to get this one, this P frame, as the reference frame for this B frame. Then we have to change this position of this P frame from this location to this location, right? We have to change this one, right? Again, for this P frame, we can get this B frame as a reference frame. Then we cannot get this B frame as a reference frame for, sorry, no, this one, right? We only consider the previous one, right? For this P frame, we cannot get this B frame as a reference frame. Then this I frame should be the reference frame for this P frame. Then we have to change the location of this P frame from this point to this point, right? For this P frame again, let's say for this B frame, we cannot get this B frame as the reference frame for this one. Therefore, we have to consider this I frame as the reference frame for this one. Then we can take this P frame as the reference frame for this B frame. Then we have to change the location of this B frame, this I frame to from this point to this point, right? We are moving this I frame from this point to this point. For this P frame, we are moving this P frame from this point to this point and reordering. We are reordering these frames, right? Because we cannot get B frames as the reference frame for another B frame. We only get for B frames, I frames and P frames for reference. For P frames, we are only get I frames as the reference frame. That is the main reason we are reordering these reordering these frames or these pictures, right? This is another example. This is the frames, original frame sequence, I frame, B frame, P frame, and so on. These are the original order 1, 2, 3, 4 up to 30, right? But we have to reorder these frames because for find out the reference frame for each other. Therefore, we have to change this B frame from this point to this point because we cannot get this B frame as the reference frame. We cannot get this B frame as the reference frame for this one. Then we have to get this one, this I frame as the reference frame. Therefore, we have to move this B frame from third position to second position, right? From this one, for this one. For the P frame, this one, for this P frame, we can get only I frames as the reference frame. Then we have to move this P frame from this point to this point, right? Therefore, we are moving this fourth position P frame to into the third position, right? And so on. We are reordering those frames for find out the reference frame for each other, right? Right. I hope you understood this concept, right?